All right, in this video, I thought I would take a look at applications of the derivative. So that's going to be mostly the curve sketching stuff that we did. So let's go ahead and look at one of these problems. So on this one, we needed to find the absolute extrema on the closed interval. Why don't we look at 29? Okay, let me get into my actual PowerPoint. Oops, let me get the right pen. Okay, so let's look at 29. So extrema, you should be thinking I need the first derivative. So then you're going to come in, this is 29, and do the first derivative. Okay, so the first derivative would be 3x squared minus 2 would come down. That would give you minus 3x. All right, and the extrema are going to be where that first derivative equals 0. So I'm going to factor out a 3x, because when it's in factored form, I can then see that there's going to be two spots. One of them is going to be when x is 0, and one is going to be where x is 1. Okay. So now what I'm going to do is I have to consider those locations. I might have to consider those locations if they're in the interval. And I also need to consider the endpoints. So now I have to evaluate the function at the endpoints and any places where the first derivative was equal to 0. So I'm going to have to check those four values. And when I'm checking it, I'm plugging it in to the original function. Whichever one winds up being highest, that's going to be a max, and whichever one's the lowest, that's going to be a min. Okay. All right, so I'm going to plug in a -1 qubit, and then minus 3 squared, 3 over 2, with -1 to the second power. So that'll be -1 minus 3 halves times 1. So that'll be -5 halves. Okay. When I plug in a 0, I get 0. When I plug in a 1, I get 1 to the third power, which is 1, minus 3 halves, get 1 to the third power, minus 3 halves raised to the second power would be 1 minus, oh, no, I did that wrong. I did that completely wrong. Hold on. I was getting distracted by something. Let me try that again. So I want to evaluate at 1. I'm going to get 1 to the third minus 3 halves times 1 to the second power. So that'll be 1 minus 3 halves. And then 2 halves minus 3 halves would be -1 half. So far, these are the values I have. Now I'm going to plug in 2. Get 2 to the third minus 3 halves times 2 squared. So that's 8 minus 3 halves times 4. So that's 8 minus 6, which is 2. Okay, so then the biggest one is that. So the absolute max on that closed interval would be the ordered pair 2, 2. And then the min would be the smallest one, which happens to be the other endpoint. And that would be the absolute min. And that would be at -1, -5 halves. Okay. And it could have been one in between. Sometimes that happens. So you have to check the critical numbers, and don't forget to check the endpoints. And then the highest, the one that had the highest y value is your max, and the lowest y value is your min. And you're guaranteed to have an absolute min or max on that closed interval. So that's the idea there. All right. Next, we're being asked to find the intervals on which the function is increasing or decreasing. So that's going to be a first derivative type problem. Why don't we go ahead and look at 29, because the format's the hardest one. So on 29, the original function was in factored form. Okay. So doing the derivative might be a little harder. You could multiply everything out if you're careful, FOIL out x minus 1 times itself, then multiply through by x plus 3, or just do the product rule. 2 times x minus 1 to the first times the derivative of the inside times the second function as is, plus the derivative of the second function times the first function as is. All right, now here's the thing on this you might want to remember. You ultimately really would like your final answer to be in factored form. So a good way to simplify this is to factor out the x minus 1 that's common. See what's left. If I take out an x minus 1 from here, I would have the 2 and the x plus 3 left. And if I take out an x minus 1 from there, I just have one x minus 1 left. Okay. And so x minus 1 and then 2x plus 6 plus x minus 1 becomes 3x plus 5. Okay. Now you could also take this expression right here and get it all multiplied out, collect your like terms, and then factor, but that would require that you understand how to factor. So I'm going to show you that part because you might be more comfortable doing that than this factoring out step. If I FOILed x minus 1, this part, x minus 1, x plus 3, I would get x squared plus 2x minus 3. Okay, once I collected my like terms. And then x minus 1 squared, remember, is x minus 1 twice. So that would be x squared minus 2x plus 1. So then I could distribute my 2 on that first part and then work on combining my like terms, 3x squared plus 2x minus 5. But then you'd have to be able to factor that trinomial. Right? It doesn't come out already in factored form. So you'd have to go through the process and say, that would work. Whatever I put here has to be 3x squared. Whatever I put there has to be 5. And I need to put them in the right spot so it's possible to get a 2x in the middle. And there you have it. So that's an option. Okay. And we wanted it in factored form because once it's in factored form, we can figure out where it's equal to 0. So f prime of x would equal 0 where this, that's a 3x, where this equals 0. Okay, and that would be where either x is 1 or x is negative 5 halves. Okay, one of those two spots. All right, now you're wanting where is it increasing or decreasing. So at those locations, it reaches a max or a min. So you need to test spots. That's a 3 on that one, isn't it? Okay, so you need to test a spot to the left of negative 5/3, like negative 2. Okay, in the middle, like 0, and to the right, like 2. Okay, something easy. These are your maxes and mins location, but you don't care about that. You want to know where it's increasing or decreasing. So what you're going to look at is the sign of the first derivative, right? So I'm really going to be looking at this factored form right here, and imagine plugging in a negative 2. First factor would be negative, and so would the second. Okay, so that means the function's increasing there. When I plug in a 0, I'd get a negative times a positive, which is negative. So it's decreasing there. And when I plug in a positive 2, I'd get a positive for the first factor and for the second factor. So it'd be increasing there. Okay, so where is it increasing? It'd be increasing on the open intervals from negative infinity to negative 5/3, and then also past 1 to infinity on those two, and it'd be decreasing in between the two critical numbers. So negative 5/3 to 1. Okay? And they might only ask you for one or the other, so just watch what they want you to do. All right. Another curve sketching thing we had to do was getting points of inflection. That was section 4.4. Second, I see points of inflection. I know this is first derivative. So extrema, those are maxes and, I can't believe I said that. Second derivative. So extrema, maxes and mins, they're first derivative. Points of inflection, they're second derivative. So if I'm asked to do a problem like, say, number 16, I would just take that and I would just do the first derivative first. And then I would do that one more time to get the second derivative. Okay. And then I need to know where the second derivative equals 0. So I'd set that equal to 0. And I'd find out that happens when x is 2. So this is my possible point of inflection. Okay. So I need to test the concavity on either side of that possible point of inflection to make sure it changes. To be an actual point of inflection, the concavity must change. So I'm going to look at the sign of the second derivative on either side of 2. So if I plug in a 1 into here, I'm going to get negative 6 plus 12. I'm going to get a positive 6. Positive is all I really care about. So that's going to be concave up like a cup. And then if I plug in a 3 over here, I get a negative 18 plus 12, or negative 6. So I get a negative, and that's concave down like a frown. So the concavity did change. So this is a point of inflection. And the last thing I need is the y-coordinate of that point. Now look, don't plug the 2 into the second derivative. You'll just get 0. To find the y-coordinate of that point, you plug it into the original function, plug in 2 for x, and you find the y-coordinate matched up with it. All right, so that turns out to be negative 8. 6 times 4 would be 24, minus 5, and that's going to give you 11. And so your point of inflection would be 2, 11. Okay. All right, now 4, 5, I actually covered that when we did limits in chapter 2, but we actually used it again when we got to curve sketching, because when you're looking for where the limit of a function as x goes to either positive or negative infinity, you're actually going to be looking at the end behavior of a function, really. You know, what happens as your x's get really, really big or really, really small is showing you what the end behavior of your function is. And that gives you your horizontal asymptotes, if you have one, or slant asymptotes, or even other interesting ones. So the official way to do it was to take the x to the largest degree in the denominator and divide everywhere by it. I'll remind you of the shortcut in a minute. Okay. Minus 4 over x. And then if you imagine, let me go one more step, simplifying. Then we have 7 plus 6 over x, and then 9 minus 4 over x. Now, if you imagine plugging in infinity, 6 over x is going to go to 0, and so is 4 over x. And we're left with just 7/9. That would be your answer to 19 that way. But when we used it for curve sketching, it means that you're going to have a horizontal asymptote at y equals 7/9. Okay, the end behavior was 7/9, means the function approaches y equals 7/9. Okay, now the shortcut was, if the degrees were the same like they are there, you could take the coefficients out in front. Let me erase that. If the degrees are the same, you can take the coefficients out in front. So y equals 7/9. All right, let's look at 21. See how the degree on top is 2 and the degree on the bottom is 3? That means this one is going to have, when you plug in negative or positive infinity, this one's going to go to 0. So that would mean you'd have a horizontal asymptote at y equals 0. Your answer to this is 0 because the degree on the bottom is bigger. Okay, so degree bigger here. Bigger degree in the denominator. Anytime that's the case, denominator, then you're going to have a horizontal asymptote at y equals 0. All right, now this one's a little tricky because it's got that, quantity being raised to the 1/3 power there in the denominator. So you see, this is really the limit as x goes to positive infinity of x plus 1 over the cube root of x squared plus 1. So the degree is kind of camouflaged a little bit, but you could still use the degree idea as your shortcut. On top, the degree is 1. On the bottom, the degree ultimately, so the top is really this. The bottom, the degree is really that. It's really a 2/3. But you can't, it's not equivalent to you just applying the 1/3 to each, but that does tell you the degree of the expression in the denominator. So see how it's bigger on top? Then this limit is not going to exist. It's going to approach, in this case, positive infinity, since x was approaching infinity there. All right. Now, the way we wound up doing this when we did it officially was we divided the top and bottom by the largest degree in the denominator. Okay. So that would be, I'm going to divide by the cube root of x squared, top and bottom. So I'm going to go ahead and squared. And then this would be 1 over the cube root of x squared. Okay. All right. So in the denominator, then I could put that together under here and have x squared over x squared plus 1 over x squared. And then on top, let me just leave these the way they are for a minute longer. And I haven't done the limit yet, so let me remember to get that limit back in there. Okay. And so in the denominator, what I really have is 1 plus 1 over x squared. On top, I have 1 over the cube root of x squared there. And then this one has an x over the cube root of x squared. Still haven't done the limit. Oh, get that limit in there. Limit as x goes to infinity. All right, so here's the deal. I know this is going to go to 0. I know that's going to go to 0. So my denominator is just going to be the cube root of 1, or 1. When I put the infinity in this denominator, it might help you if you remember that this can be simplified. Let me simplify it. One more stretch. This is why we like shortcuts, because it's so tedious. This right here is really x to the first over x to the 2/3. And you can subtract those exponents. That would really be an x to the 1/3. X to the 1 divided by x to the 2/3 would really be x to the 1/3. So what I'd really have at this point is let me move it over a little more because I may need one more spot. Let me go to here. So I'm trying to do the limit. That first term really simplifies to be the cube root of x. And then I have this still. Okay. Let me go back to the original. And then here I have the cube root of 1 plus 1 over x squared. 1 over x squared. Okay. And I'm looking at x going to infinity. So this goes to 0. That goes to 0. This goes to, that's like an infinity in there. And the cube root of infinity is still infinity over 1 is still infinity. Okay. And it would be positive infinity because it was positive here. This had been negative infinity. The cube root of negative infinity would be negative. Okay. Either way, it's really that it doesn't exist, right? But when it's an infinity, we use that notation to indicate that it's going to infinity at the end. All right, but back to the beginning. Basically, you have x to the first on top, and you have x to the second raised to the 1/3 power on the bottom, bigger on top. Then the limit doesn't exist. And the function is going to approach either infinity or negative infinity, depending upon what you're plugging in and what happens when you evaluate it. Okay, so in this case, it didn't exist and it approached a positive infinity. All right, that's probably going to be harder than you get, I would guess, but we'll see. All right, and then one more section. This 4.8 was kind of an odd little thing. Find the differential dy of the function. All right, so with that one, it's basically, when we do the first derivative, we're doing this. So like y prime equals that, dy dx. So we're basically going to do the first derivative, but we're going to pull the dx over to the side. So like if you had a problem like what well, any of these are fine. Let's just do one. Then it's basically, can you do the first derivative? So the first derivative of that would be 1 times tangent x plus x times secant squared x, okay? And that would be the dy dx notation, the way we did it before we had this section. That's what it would be. So when they say find the differential, it's like you're solving for dy. So you multiply by dx on both sides, and you get that dy would equal tan x plus x secant squared x dx. And there you have it. So it's really just taking the derivative and then moving that dx over to the right-hand side. And then it's just which problem you get, you have to make sure you know your derivative rules. Like you'd have to be able to do the quotient rule there, and here you'd have to be able to do the chain rule. So like for 27, you would rewrite first. So that's to the 1/2 power. Then you could come in and do the derivative like normal. 1/2, 9 minus x squared to the negative 1/2. But you do the derivative of the inside and get your negative 2x. You might take a moment to clean that up. So 2 and negative 2 would be just negative x. This would be in the denominator now as the square root of 9 minus x squared. So you know your dy dx equals that. So taking the derivative is the hard part. Then you just have to remember for the differential form to multiply through by that. Okay, get the dx over here. And they're doing that because right after this, we get into chapter 5, we get into integration. And this is what we're trying to undo. We're trying to integrate that to figure out what y is. So they're just exposing you to that notation. Okay.